So welcome everybody to our CCNP class. Today we're going to talk about Eigrp and hit some Ospf stuff. Remember, in this particular CCNP class, we don't have to know how to actually even configure Eigrp. We just need to know about Eigrp and how Eigrp works. One of the things I want to ask you is, give me Eigrp. Give me something you know about Eigrp. What kind of protocol is it? There's multiple answers to this. So when I say Eigrp, obviously it's Enhanced Interior Gateway Routing Protocol. So by default, we know it's an IGP. So we know it's an Interior Gateway Protocol. And what does that mean? When I say it's an IGP versus an EGP, which is an Exterior Gateway Protocol. Anybody? Nick or Michelle? There's only two of you here, so one of you. Any idea? Well, IGPs route within an autonomous system. So they're designed to route inside an AS instead of between ASs, like exterior gateway protocols, and our interior route within an autonomous system. Remember that an autonomous system is a group, or an AS is a group of routers under the control of a single admin, typically all running the same IGP. So other IGPs would be ISIS, RIP, Ospf. Those are all IGPs. EGP, by the way, the only one we use and know of, well, the only one we use is BGP. There's actually a protocol called EGP, but we don't use it. In addition to this, there are two main types of interior gateway routing protocols. There is the distance vector routing protocols. And what's the other one?
Link state.
Link state. Okay. Eigrp is a distance vector routing protocol. And the reason it is, even though it uses a huge number of link state concepts, is because the biggest thing is it's called routing by rumor. In other words, even in Eigrp, the routers only see from the neighbor's perspective. In other words, the routers only exchange information with the directly connected neighbors. They don't exchange it with everyone like with link state. In link state, you flood out your link state advertisements and you have a holistic view of the topology. Even though Eigrp is very fast to converge because of some link state features it uses, it still only sees the network from its neighbor's perspective. So it is still a distance vector routing protocol. So we're going to look at Eigrp, some of the fundamentals. We're going to look at the metrics and how it uses metrics and how that metric comes to be calculated. And we'll look at some route summarization. But here again, autonomous system is a group of routers under the control of a single administration, typically running the same interior gateway routing protocol. Here's an example of two ASs, Eigrp. Now I will tell you this, even though when we configure Eigrp, we use router Eigrp, and the command even says AS. That's really not an AS number. It's really just a process ID to hold that information inside of the memory for a router. There is a very important thing they state: if you're going to be using Eigrp and you're running BGP and you have an assigned autonomous system number from an assigned numbers authority, they say to use the same AS number for Eigrp as you're using for BGP. If you don't have a BGP autonomous system number, the main idea is to use autonomous system number 1. It is important to note that in order for a set of Eigrp routers to exchange information, they must both or must all use the same autonomous system number. Otherwise, they will not form a neighbor relationship. A couple other terminologies that are important for you to know is successor route. That's the best route to a path. So it's the route with the lowest metric, lowest path metric. And then the successor is the first next hop router for the successor route. It's known as the successor. And then a feasible distance is the metric value for the lowest metric path cost to a destination. So it can be, basically they're showing here, it's calculated using the different costs here, 256 plus 256 plus 2816, which is the cost on the 1044 network, which is the successor route for R1 to get to 1044. And then reported distance, which is the distance that your neighbor reports is their feasible distance for the advertising router. So in this case, you'll see it's 2816 plus 256 because the reported distance is 3072. We're going to learn about what's called a feasible successor, and a feasible successor will have to meet what is known as the feasibility condition. And that is the, I've actually got a little thing over here that feasibility condition, the reported distance must be less than or equal to the feasible distance of the current successor. And that is important because that means it cannot go back through the router. So let's look at this, okay? Why is this route 2560 a feasible successor? Well, let's first look at our best route. Our best route is 3328. Okay, so that's 2816 plus 256 plus 256. So we're going from R1 to R3 to R4 to get to the 1044 network from R1. So that's our best route because we add 2560 to 2816. Obviously, that's much more than 3328. But now we're going to look and see, okay, my feasible successor, does this network across here, does it meet the feasibility condition, which is the reported distance is less than or equal to the feasible distance of the current successor route. So when R4 reports its feasible distance to the 1044 network, it will be 2816. Okay, and because of that, and you look at it, it's less than the best path of 3328. So in other words, if I go from R1 to R3 to R4 to get to this network, the best metric is 3328. R4's reported distance to 10444 is 2816. So there's no possible way that this route from R1 to R4 using this link, which has a metric of 2560, there's no way that route is back through R1 because it's less than the best feasible distance, this feasible distance here. So the reported distance of R4's secondary route meets the feasibility condition because it can't go back through R1 using this route because it's already less than that route. And that is how it becomes a feasible successor. The important thing for EIGRP is this. If you have a feasible successor in the routing table or in the topology table, it's not in the routing table, it's in the topology table, it can immediately become a successor if the successor route fails. So that is an important item that makes EIGRP very, very quick to converge. Now, if there is no feasible successor in the topology table, well, then you have to go through a full set of the dual algorithm and figure out your next best successor route. Okay. A couple items I want to mention to you is that EIGRP has 3 different tables for each prefix that is enabled. So by that I mean each address family that's enabled. So when we look at EIGRP, EIGRP has a neighbor table, it has a topology table, and it has a routing table. Okay, and that's for each AFI and AFI, which is address family identifier, and SAFI, which is subaddress family identifier, which basically just means this. It's for IPv4 and IPv6. So if you're running both, then you can have up to 6 tables. So one each neighbor topology and routing table for each of these address families, IPv4 and IPv6. Show IP EIGRP topology will show you the topology table. You can see the successors. A couple of other things that are very important about EIGRP is by default, it does do equal cost load balancing for up to 4 different links, min path of 4. It also is one of the only routing protocols we have that can actually do unequal cost load balancing using the variance command. Okay. So here's our different packet types: hello, request, update, query, and reply. Also, just so you know, EIGRP actually has its own protocol. It is, in fact, protocol 88. And it uses RTP, or Reliable Transport Protocol, which is protocol 88. A couple other little things that, wow. Can't even believe I actually did that. I like protocol. All right. A couple other quick things to note is in IPv4, it uses 224.0.0.10 as its multicast address to send information to. And in IPv6, it uses FF02::A, which is 10 for IPv6. It's communicating. So those are just some things to use to help you kind of know some of the basics about EIGRP. Hello, type 1 packet. 2 is a request packet, which is sent reliably. Update is sent reliably. Queries and replies are typically sent unreliably. Also, hello packets are typically sent unreliably. Here is the classic EIGRP metric formula. Here's what you need to remember. You're going to be asked which one of these K values are set to 1, which ones are set to 0. By default, K1, which is bandwidth, and K3, which is the lowest delay, the sum of the delays on the path, are set to 1. So when you really look at a classic EIGRP metric, it's bandwidth plus the sum of the delay, and it's the lowest bandwidth in the path plus the sum of the delay, because everything else is a 0, so all these other things end up being 0. So bandwidth is the slowest path scaled to a 10 gigabit link. Delay is the total measure of delay in the path in tens of microseconds. You will be asked this somewhere on the exam: what K values are set to 1, which ones are set to 0. So by default, you will see it is that. You've got K1, K3, which is bandwidth, lowest, and the sum of the delays. The reliability and all the other K values, K2, 4, and 5, are set to 0. There's even a K6, which is used with the expanded EIGRP metric, but it also is set to 0 by default. Actually, it's not even used by default. Questions about this metric? So with each prefix, you will still have hop count, cumulative delay, minimum bandwidth, link speed, and reliability, but only the lowest bandwidth and the sum of the delays are used in the calculation. Questions? Okay. You will notice some of the problems with EIGRP, which is very similar to the cost problem we find in Ospf, and that is a gigabit and a 10 gigabit basically have the same delay associated with them. All right, the good news is the bandwidth is different. So it does count the bandwidth, and you end up with the metric being correct because of that. The other thing here is if you need to differentiate between an 11 gig and a 20 gig interface, you can use the wide metric. So you can actually put in the command, which is, I wrote this command down. Well, I thought I did. Yep, no, I didn't. Yeah, metric rib scale. you can actually do metric grid scale on a global command, and it will actually turn on the wide metrics. I told you that by default, EIGRP does load balance among equal cost paths, up to 4 by default, as long as they're equal cost. Remember, the first item in all routing table entries is the administrative distance. The second item is the actual metric. So here we have an example of a EIGRP doing equal cost. Actually, no, it's not. This is topology. They must be using a variance multiplier. Yeah, they are. They've done the variance here. So they're doing unequal cost load balancing. So this is unequal cost load balancing. And you'll notice they use the variance of 1.6 to change the variance, actually the variance multiplier of 2, so that it would be within the variance. So that's the neat thing about EIGRP, is it does support unequal cost load balancing, which I still think has some, I don't know. I'm not sure that to me has as much usability as they make it out to be, but it is what it is. All right. I want to show you this. I made a notebook here where I'm studying for different things myself. And so this was a really good picture out of some studying that I'm doing. In order to form a neighbor adjacency, 2 EIGRP devices must have the same AS number, the same metric values. In other words, if you change any of those K values, which you can change them, remember by default, what 2 are set and available? Okay, 1, 2, 3, 4, or 5 are actually used in the metric by default. Okay, 1 and 3. Yep, there you go, Michelle. Very good. K1 and 3 are used by default. So K2, 4, and 5 are not used. They must be on a common subnet. And if you use authentication, the method and password must be the same, because EIGRP does support authentication. You'll get a neighbor adjacency. The other thing that I've done enough of these exams to know that little things like this, I know multi-protocol support is built into EIGRP, so it supports IPv4 and IPv6. But this little line was thrown in here, and it was also a question on the end of content for a page I was studying. So I would probably commit that to memory. It can also be used as to distribute dial plan information for large-scale WAP networks using Cisco Unified Manager. So just wanted to throw that out there because that is important. I think you probably already know enough about EIGRP to know that it uses partial bounded updates. In other words, it doesn't send the entire table out. It only sends out changes once the original original tables are exchanged. It does not send out an update every 30 seconds like RIP does. It only sends it out when there is a change, which helps with reducing bandwidth use. It is classless. It is very fast to converge, and it uses the dual algorithm. Other than that, EIGRP is pretty simple. One quick thing, true or false, EIGRP timers, hello timers must match for 2 devices to form a neighbor adjacency. Is that true or false?
It's true, isn't it?
Actually false. They will actually, let me make sure of this, but I think EIGRP is the one that will negotiate. Let me make sure that's, nope, yeah, that's correct. OSPF requires they match, but with EIGRP, they do not have to match because they will actually negotiate to the lowest. Okay. So OSPF, they do have to match. With EIGRP, they do not. which is a little confusing, but it is not that bad. Route summarization, we already know about that. That's pretty much, I mean, you've done summarization with prefixes before. So EIGRP does support doing route summarization. You can do a summary prefix. Okay. Now, what I want to do now is I want to talk about OSPF.
So EIGRP still Cisco proprietary, right?
It is not Cisco proprietary. It is now an open standard, except for, I read today, I was looking that up. It is an open standard now as of 2013, but the stubby area, wait a minute, let me think about it. Yes. The stubby area portions of EIGRP there are some portions of EIGRP that are still proprietary. But it is actually now an open standard. And I say that, but it is open. It's actually now, it's open. Published it in 2016 as an informational status. So it's an open standard in 2013 and has an additional in 2016. But there was a couple feature sets of it that are not open standards.
I was just trying to see if I could find a router that supported it.
Yeah, I don't think there's any router that supports it other than maybe some versions of Linux routers that support it. I would still say that for all practical purposes, EIGRP is Cisco proprietary. Having said that, if your network supports it, it is a good protocol. All right. Now, Cisco will make you think it's the best protocol, but let's not go there. It's, you know, OSPF still has a lot of, in fact, I was looking at the timers. There's a timers thing, and it shows that OSPF with its tuned timers is actually faster than EIGRP when you get a lot of routes, but it's real close. I mean, EIGRP does a good job. With the default timers of OSPF and no tuning of OSPF, EIGRP beats the pants off of it. So I thought that was kind of interesting. All right, EIGRP questions. Let's talk about some simple OSPF. Then I want to show you a couple things on how to do some OSPF configuration, because we actually do have to know how to configure OSPF. So OSPF, open shortest path first. It is an open standard link state protocol, which means it is going to have a complete view of the network. We're going to look at how to configure OSPF. We're going to look at the two main versions, OSPF v3 and v2 and v3. V3 does support IPv6. So link state advertisements, the link state database, and the spanning tree. So the OSPF uses link state advertisements, which means they're sent out to all the routers on the network. They're sent out as LSAs, and we're going to talk about different LSA types because there's LSAs 1 through, really there's a bunch, but we talk about 1 through 5 and 7s in this particular course, but there's even more. But using these link state advertisements, the routers then build a topology table, very similar as far as topology goes to what they do and what EIGRP does. But then OSPF uses the cost of the links based upon the bandwidth of the link to find a loop-free best path to each network. And then it uses that to build its shortest path first tree to all the different networks in the internetwork. OSPF must always have an area 0, and that is the backbone. And then there can be other areas that are able to be connected to the backbone. And you can use this to allow for network changes within an area not to affect all the routers in other areas. So a properly defined OSPF network can actually have links flapping over here in area 12, and it will have 0 effect on area 0 and area 34. They will not have to run through a shortest path first algorithm. They will not have to do any type of route table lookups at all. They would just not even know there was a problem with the link over in area 12. For this reason, OSPF is extremely scalable. Now, OSPF uses 224.0.0.5, which is all routers, or 224.0.0.6, which are designated routers, or DRs. DRs are used in multi-access networks such as Ethernet, and we'll talk about that because it will keep each router from having to create adjacencies with every other router in a multi-access network. So, type 1 OSPF are hello packets, and they are used to discover your neighbors, obviously, and they're sent out to create that neighbor relationship. Type 2 are database descriptor packets, which summarize database contents, and they're used, they're exchanged to describe what's in the link state database. A link state request or a type 3 request part of a database. So it can either say, hey, I need to know about a particular network, or I need to know about anything that has changed. A link state update is typically a direct response to a link state request. And then a link state ACK is a acknowledgement. So, hey, it says, yes, I received this, or I have received an update from you, or a list, or other items that could be sent via OSPF. So our hello packet contains what is known as a router ID. The router ID will be the highest IP address on any loopback interface. Well, first off, it can be set statically. So if it's not set statically, it is going to be the highest IP address on any loopback interface, or the highest IP address on any physical interface that is up. So typically, though, we set these so that we know exactly what our router IDs will be. If you don't have a router ID, by the way, OSPF cannot start and cannot run. The hello has any authentication options. So just like Eigrp, OSPF does support authentication. It will have the area ID, so whether it's area 0, 1, 2, whatever. The mask priority, this is used for DR election. We'll talk about that when we get there. Hello interval, dead intervals. And if it is a BRDD or BDR on a multi-access link, it will be in there. And a list of the active neighbors on the segment. These are the neighbor states you can be in down. So the initial state of a relationship. No information has been sent, so attempt has been made. Init, a hello packet has been received from the router, but bidirectional communication has not been established. Two-way bidirectional has been established, and BDR-DR election will take place in this particular, at this point if it's needed. In other words, if you're on a multi-access network. XStart, so they've started synchronizing the LSDB and determining master slave for who is going to do the LSDB synchronization. Exchange, routers are exchanged using database descriptor packets, loading, and full. One of the things you'll see sometimes is what is called stuck in a init. OSPF, if for some reason there's a link that is only allowing one-way traffic, bidirectional traffic cannot be established, you may end up with a router what is stuck in a init, which means that you need to check to make sure you've got bidirectional communication. Here is the concept of DRs or designated routers and backup designated routers. In a multi-access network, each router would have to form an adjacency with every other router, which can make the neighbor table and the adjacency table get huge very quickly. So instead of this, what happens on multi-access networks is OSPF elects a designated router. Then all of the devices on that multi-access network form a neighbor relationship with the pseudonode. All right. So instead of having to do it with every single router, which gets crazy as you put a large number of routers in a multi-access network, they form just a relationship or an adjacency with the pseudonode, which is that designated router. The DR then takes in LSA 1s and we'll turn back around and send them back out as LSA 2s. And we'll talk about that when we get there. But basically, it allows for better use of bandwidth and resources on multi-access networks. So let's go do some configuration. I want to go and show you over here in NetLabs, we're using this setup. All right, so I'm not going to use the actual lab itself, but we are, I'm not going to use the actual lab content, but I am going to use the initial setup. So what we've got here is D1 set up with the 10.10.8.0 and 10.10.9.0 networks on G123 and 1023, 1024. And R1 is connected to this multi-access network here, which is 10.10.0.0/29, and is available on to D1, D2. So what I'm going to do first is I'm going to use just the typical method of setting up OSPF, and I'm going to use a network statement to have this network placed into R1's OSPF configuration. So first off, I'm going to show IP int brief to ensure that the 10.10.0.1 is indeed there. Show int interface G0, G0, 0, 0. Make sure /29. /29 is actually assigned to it, which it is. Okay. So I will okay. I'm now going to do this. I'm going to do config T, router, OSPF. Now, you'll notice the next item is a process ID. So process IDs do not have to match on two routers that are going to form OSPF neighbor relationship, but I'm going to make them all match here. Router OSPF 1. All right. Next thing we're going to do is we're going to put a network statement. So network 10. I remember my network. 10.10.0.1. So 10.10.0.0.29. Now, I know the next thing it tells you to use is a wildcard mask. And on the exam, you need to use wildcard mask. So if it's a 29, that'd be 255, 255, 255 dot, let's see what, 192, 224, 248. All right. So that would be a dot 0.0.0.7 area 0. Okay. Now, you could also, in the real world, you can just put in the subnet mask and it will do it for you. Don't do that on the exam. Okay. But in the real world, you can actually just put it in and it will do it for you. So now we can do a do show IP protocol. Let's see what we got. Well, if you don't hit the wrong button like 3 times there, Kelly. So we've got OSPF running and we are routing for this network 10.10.0.0.0.7, which is /29 network. I'm going to go to D1 and I'm going to use a different method. This is a method they don't teach you about in the curriculum. So I wanted you to know it because I think it's a really cool method. I would like to advertise all the networks on my entire device. So I'm going to go config T, type IP routing because we've got to turn on routing first. It should already be on, but let's just make sure. Router OSPF 1. And I'm going to make a network statement of 0.0.0.0.0.0.0 area 0. Now, what should happen here, it's going to take it a little bit, but you'll notice we went from loading to full. So I do a do show IP OSPF neighbors. You'll see I have a neighbor in 209.165.200.225 full DR. So that my neighbor is the designated router for this particular multi-access link. The address is 10.10.0.1, which you will notice is R1. So what I just did, do show IP pro, is I just advertised every single network on my device. And if I add a network, so let's go over here to R1 right now and do a do show IP route. We should see the OSPF routes of 10.10.8.0, 10.10.9.0, and those are coming from 10.10.0.2, which is D1. So that was one way to do it. Just say everything, all interfaces on here are part of area 0. So the neat thing about this is if I go back in now and do loop back 0, and do IP add 172.16.0.1, 255, 255, 255. 0, no shut. I can go back over to R1 now, hit the up arrow, do a show IP route. We should now see 172.16.01 because every single network that I put on D1 will be advertised. So that's using that quad 0, and you'll see how it shows up in here. So that's one way to do it. The other way we showed you obviously is on R1, we used just the actual network statement itself. So we made a network statement for the one network we wanted to advertise. The other way we can do it, if we look at R1, so we say we want to advertise loopback 0 into OSPF area 0. So what we could do instead of putting in a network statement is we can actually do this, int LO0, IP OSPF. We do our process ID area 0. Now, this, do a do show IP. We should see that the network here is being advertised and the network assigned to loopback 0 is now being advertised. So we should have the 192.168.1.0/26 network down on D1. And it's not there yet. Oh, wrong one. Okay. I didn't do 192.168. I did the wrong one. I did loopback 0 instead of loopback 1. Oops. So the 209 is there instead of the 192. Let's fix that because that's a screw up. So let's go up arrow a couple times. Let's do no IP OSPF 1 area 0. Let's go int LO1 IP OSPF 1 area 0. Boop. Okay. Oh, I'm in the wrong one. Golly. Int LO0. I cannot type tonight, y'all. Control A. No. Int LO1. Now, let's try this again. Now we should see the 192.168. There it is, 192.168.11. Sorry about that. The other thing we can do is we can do IP route 000 int LO0. All right, I know I'm not that dumb. Yeah. Yeah. There, I was putting it in there like a doofus. Now this, obviously we don't normally do loopbacks as our outgoing interface, but that works okay. What we're going to do now is we're going to go into router OSPF 1. We're going to type in default dash information originate. And what this will do, it will now bring in an external route, which is an external OE2, which is an external route that will show the route coming from R1, and it's basically redistributing a static default route into this. Now I'm going to cheat on D2. I'm going to make it easy for myself. Again, router OSPF1, IP routing. I guess turn on routing first. Router OSP. By the way, if it's not turned on, that's what it will tell you. OSPF1 network 0, 0, 0, 0, 0, 0, 0, 0. I'm gonna cheat, make it easy on myself. Okay, so we're gonna advertise everything into here, and now we should see do show IP. Wow. As soon as we get a full loader, you'll notice we get our E2 route from R1, and we also start getting our other routes from 10.10.02. And these are the route, that's that loopback that I put on to 10.10.02. If we do a do show IP OSPF topology, you'll see that we have our router ID here, okay, and our process ID. We also can do show IP OSPF. If we do neighbors, we see that now we've got that router 1 is our DR, router 2 is, D1 is our BDR, our backup domain router, which, by the way, the backup designated router. The BDR, it will take over if the DR fails. And now what we can do, by default, the router with the highest bridge ID, or excuse me, the highest router ID becomes your DR. We can also control that with the priority. There's a way to control it so that the higher priority will become your DR if you didn't want router 1 to be the DR for some reason. Do show IP approach. Show that. You can see, again, there's our router ID. It pulled the highest IP address on any physical interface. If you wanted to change that, you could go to router OSPF 1 and do router ID 3.3.3.3. However, you'll notice it will not take effect until you clear your IP OSPF process. Now, if you do this on a production router, let me warn you, this will drop the routing tables for the router and it has to be rebuilt. So don't do this. It has to also reestablish all its neighbor relationships. So unless you are certain you want to do this, don't do it on a production router. Now, if I do a do show IP approach, you'll see that my router ID is 3.3.3.3. So I can also do router ID here, 1.1.1.1, do clear IP OSPF process. Let's go to D1, do router OSPF1, router ID 2. Now, do show. You should see there's been a change, or will be a change eventually in the DR BDR. Let's do it. There it went. We see that neighbor has actually dropped out, so that's gone now. So you'll actually see that our DR now has become D1 instead of R1. Now, a druther is neither a DR or a BDR, but it can be a DR if it needs to be elected to become one. Okay, so you'll see at this point, D2 is the DR and D1 is the BDR, and R1, because it now has the lowest neighbor ID, is the druther. So it is no longer the DR. The highest router ID became the DR. Right? Questions about the different methods of how we can do our OSPF networks. So let's do it again. OSPF networks, all connected using quad zeros. Network statements with wildcard mask, real world use your subnet mask. And then assign interfaces to. All right. So that's how we can do our network statements. We need to do those. Okay, folks, I'm going to call to stop there for today, and we'll come back and do some more of these. But this is interface. I mean, exactly what we're talking about here: network statements, interface config, setting the router ID. I didn't do any passive interfaces, but this is something we can look at just for real quickly. You'll notice that on D1, realistically, there's no reason to be sending out hello packets on 80 or 90. So on D1, there's a couple things I could do. I could do passive interface G1/0/23, okay, and 24. Oops, 24. And then now what you will see is on the topology here, hello packets will not be going out 23 or 24, and there's no other OSPF over here, so you don't need that out there anyways. That's actually the correct way to do this. So do show IP protocol, and you'll see what your passive interfaces are right here. Now over on D2, another way you could do this is this: you could do passive interface default. But the problem with that, if you do, notice how you just knocked all your neighbor relationships down because you inadvertently stopped G105 from being passive. So what you want to do then is go no passive interface G105, do show IP prot, and you will see now that by default all interfaces are passive except for G105. And now D2 should eventually form neighbor relationships again. Yep, there it is, starting to do the negotiation with them. So there's different ways of doing passive interfaces. You only make an interface passive if there are no other OSPF neighbors on that link. So typically all of our access links we would want to make into passive interfaces. Any questions about so far with OSPF? Can you use passive interface range command? That is a good question. I don't think so, but let's go look. Let's do passive interface range. Nope, I will not take it. No range command. Let's see if there's anything that will let us do anything like that. I mean, technically you could do, I mean, by doing the passive interface default, that turns everything off, and then you had to go and do no passive interface. But there's no actual range command that lets you do just a set. Let's try it. Let me try this. Let me try. Yeah, there's no way to do a range. Good question, though. Excellent question. If I had that, I would just do passive interface default and then no passive interface, the ones that don't need to be passive, which is typically what you're going to do on most of your distribution layer switches. Okay. Any other questions? All right, couple more people show up. Okay, everybody, keep working on the labs, keep working on the exams inside of Neticat. And I know they're just quizzes. I am caught up on grading. I can't tell you how nice it is to actually grade inside of Canvas instead of having to use the other grading inside of Neticat. So it's very nice. I'm using that in here. So if you have any questions, let me know. I also did something for you. I did put, I noticed that I did not have due dates set in Canvas for your assignments. So all of your assignments in Canvas now do have due dates associated with them. Please do remember though, those due dates are not set in stone. They are recommendations for you. We've got several weeks coming up where we have no labs due. So if you're behind, don't freak out. Just keep working, keep doing the labs, and send me any questions that you may have about anything going on. All righty. Any other questions for me? Any comments, concerns, or criticisms? I'm gonna stop the recording.